I think at least I have the for each student in the class. Okay, so last class we talked about the file structure. So there are two ways to please talk to outside. The main purpose of using database is what? To search data very fast. So especially when we have a large amount of data, it's not easy to access the data efficiently. So to address such a problem, there are a bunch of different ways. The major approach is we can use the cache data, like the buffer, using the buffer. So when we start the database system, by the way, what happened when you start up the DBMS, database system? What does that mean, startup? We know booting my computer, reboot Windows, reboot Unix. So we understand what's going on when we start up the operating system. What happened when we start up the database? Sometimes you will hear when you join the project, please restart the database and start up the boot database system or the Oracle information. What's really happened when you start up the database? Have you ever thought about this? No? So what is the DBMS, database management system? What is the DBMS? DBMS is? It's a software. It's the same as what happened when you start up any software. So what happened when you start the Microsoft Word?
Prepare the file and
it will
prepare the file.
First, your program will be loaded into the memory. It will be processed. It will create the process that to check the resource that the program need. Like the Microsoft, if you double click the home of the Microsoft Word file, check whether the file is available, then it will be loaded and display the file. Almost the same thing happens when you start up the DBMS. So when you start the database on the operating system, it will create the processes, a lot of processes on the memory. Sometimes their job is very, very critical, and so we assign that this process is for the writing only. This process is the log. This process is the communication, and so on. So a number of processes will be created. That is the first thing. Second, the checking the resource, especially the memory. The memory, some part of the memory will be reserved for the database. Each DBMS uses a different name of this part, this memory area. For example, this is the example. Oracle called this area as the system global area. It's the dedicated memory space. This part will be used for the cache of the DBMS system. Then we can speed up. Plus, it will check any file that are associated with the DBMS. Then finally, your DBMS is running correctly. In other words, if your database has the problem, when you start up something wrong, it's not connected, check whether all the number of processes are running correctly. Check the memory space, whether memory is enough. Okay? Inside the code of your DBMS, like you are developing the DBMS system, how can you allocate this memory area? You can use the emerald. So you can specify the size of the memory. Okay? Then also you need to check the search of file. Then finally you can find the problem of your DBMS, whether they are running correctly. You can troubleshoot if there's any problem. Then at that time, so to speed up, you can use this memory area. Another way is we are going to construct different data structure. Last time we talked about this file, how to store the file. One more thing before we start the new data structure. The file data structure, do you remember this file. We have an unordered file. We have the ordered file. We can use the hash file, okay, to store the data. So for example, you can create the one file per table, like the student table. When you create table, student, blah, 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 blah. This will be submitted to the what? SQL engine. It should be compiled. Then DBMS understand what they need, the table. So create the file, or locate the file, like I'm going to use the unordered file for the student. Locate the file, then based on the column, each record has the something, the data structure, like the name is the 10, character 10 byte. Fixed length will be allocated. In case of variable character and so on. If you need more space, number of block will be physically allocated. Who knows this block? Operating system knows. So, however, most of DBMS directly access such a, because of that, sometimes DBMS is not just an application program. It's more like system program, operating system. Okay? So, because it directly allocates such a block, this is a block, a number of blocks will be allocated. So, this is the file. One more thing. This is based on the file system storage on DBMS. There is another approach, it's called the raw device. What does it mean, raw? Raw device. Cooked device. This is a cooked device. Why? We are using file system. Your storage of your table will be created on top of what? File system. What is a file system? How many of you are taking operating system just before? I know. So actually, it's not possible to separate the operating system and the database code. So eventually, when we talk about the hardware part and the file part, it's almost similar. So file system is a software on top of what? Physical hardware, like the hard disk drive and the SSD, whatever. On top of that, we have the file system. It's a high-level interface. You don't have to worry about whether I'm using SSD or I'm using the hard disk drive. You can just use the same file system, NTFS, or GFS, UFS, NFS, right? That's what you need. That's called a file system interface for hardware. But you don't have to. Then, on top of the file system, you are going to create a table as a file. This is another file, ordered file, and so on. Kind of cooked. Okay? You are using high level. However, problem of this one is a slow one. You rely on performance of your operating system. You need to know the file system and communicate to each other, controller, and takes some time. Instead, why don't we DBMS directly access the hardware as a raw device? So for example, I'd like to use this. This is our hard disk drive storage. I'd like to keep my stuff. So file system approach is like it's well the design and furniture. So I put the textbook here and the homework here and so on. To do that, you need to actually build this fancy, nice desk and design and pay a lot, right? Then use very limitedly. You need to put your stuff on the desk. However, I don't need this one. My purpose is fast, just empty room. You don't need such a decoration. Just put stuff one by one in the empty storage. Which one will be faster? Without furniture, without anything, just put your stuff. Okay? Because you don't need to spend the time and the money to decorate and put this one. Just put your stuff in the empty storage. That's a raw device. So raw device usually faster than the cooked device, which means file system. Definitely, obviously. Problem?
We cannot access as soon as possible.
We can access, but problem is It's so fast. It's hard to, right? It looks like this one. You can create the student.txt file, for example. But here, you need to understand this, and byte by byte, bit by bit, you need to process. This is a raw device. This one is faster, okay, but hard to manage. You don't know what's going on inside. Only the directory, DBMS, directory access to this one. This is a raw device. This is one of the ways how to speed up. Many mechanisms are working on the DBMS to speed up. Then, another important thing is that this is a file anyway. This is the table file. Let's consider this is a file also. Then, we can improve the performance to access data, but it is limited. It's bounded. So to overcome that, we are going to discuss about the new data structure, which is called the indexing. So I think that most of the students know what is an index. What is an index? What's an index? Index is? It's a primary usually? No, it's not primary. Our primary is in the file, data, right? For example, I have a presentation. So, but I'm usually very scared to present in front of audience or the public. So I need to prepare index card. So index card is not your primary. Your primary is the presentation, but index card will have order of your presentation. You can touch it on that with the index card. Or, for example, you have the textbook, like this one. Actually, it's not textbook, but whenever you search the specific topic, you can search. One way is you can check the TOC, the table of contents. Or you can, but table of contents usually have the what? Title. So, and then another approach is page by page, from the first page, second page, third page, until you find it. It's a simple but takes some time. It's a linear search, or brute force sequence search that we discussed on file system. Another approach is most of textbook has the index at the end of it. So how those index is composed? It has the keyword, lead, OS, and they are sorted. So like the A, okay, then binary, and the compute, and database, then plus what? Page number. Like this. Then how can you use the information, this index? First, find the keyword, compute, then number of pages, then how can you search the page number 30? First, second, third, yes? You can use binary search, right? Open the half of your textbook, whether bigger or lower or higher, then going to select half, then finally you can search. Find it. So this is called index. So as you can see, this is the
Key value.
this is value, key index, key value, and this is the pointer or address. Any index is the same thing. The index key value, indexed value, or the key value is a value, keyword, whatever the name is an indexed value. Then plus address, location, or the pointer sometimes. So this is the index. So I cannot remember the name of that. It's the index entry. So this is called the index entry. So each index entry consists of the value and the address. So using this one, we can search the data very quickly. So then, problem is, when we have a number of index key entry, how to organize this index key entry. Then store the index key entry to the file. So that is called the index file. Or this is called the index data structure. So index is another data structure. Mostly it's not the primary. Primary is the file structure that we discussed. To speed up to search the data, we can consider another data structure, that is index data structure. If we store such an index item to the file, it's called the index file. Each item has always index key value plus address. Okay, then depending on how to organize this index file, there are different index files. Different name of index. You heard about the B3 index, B plus 3, or the tree index, or the cluster index, primary index. Each of them has different ways of organizing this one. Okay. So today we will see such a index. First one, let's just a little bit speed up. We will use this. Before we start, there are two types of index. One is, let me use this example for better your understanding. So when you check your index part of your textbook, how many keywords? As the name implies, it's only key. Not all words of your textbook are indexed, right? Only some keyword, few of them. At that time, this kind of index is called sparse index. Okay, sparse index. Why? If you index all the words in your textbook, all the data, all words are indexed, it's called the dense index. In terms of data file, so we have the 100 students. Okay, 100 students, 100 record in the data file. If you index all these 100, it's called the dense index. Okay. However, if you index only few of them, is called the non-dense index, or sometimes called the sparse index. There are two types of indexes. So we will see both of them. An example: sparse index and the dense index. So then, first one is the primary index. The primary index is we are going to, anyway, main purpose of an index is to help to search the data in the file. Okay? At that time, what is the best way to search the data? When I search the student, if I describe handsome, nice, and the blue shirts, whatever, it will be hard. Instead, if I call your ID or the name, even the name sometimes confused, because there are several students who are using the same name. So when I call the ID, it's clear, and I can define the search the data very fast. So always, not always, many of the time, when you search the data if your database is well designed, and also your application is well designed and implemented, you can use the primary key of your data to search the data. However, if without indexing, we can search the data using the key. How? Binary search. You can use the binary search. Binary search is like logarithm. You remember the complexity or in terms of big notation. By the way, yesterday I actually shared the link with the data mining class only. I don't know, probably. So the link actually shows the kind of experience an interview, job interview with the 5 top company in Silicon Valley. So at the time, what he prepared, this is his experience. What he prepared, one of the important things is whether, especially in the Google, whether you know the big O notation or not. Why? Because that's everything. The key part of the Google is anyway still the search engine. Whether speed up, the more data the Google has, it's better. Problem is it's slow to search and demand. So such a little bit slightly better. In terms of the big O notation, it's a huge difference. Not only the search response time, but it's the money. It's totally related to the money. So whether you can explain something algorithm or problem in terms of big O notation. Okay? So in terms of big O notation, this binary search is a logarithm, which means it's better than the linear. That's definitely better than the exponential problem. Still, it's a monotonic increase. The more data you have, the longer time it takes binary search. So how can you solve the problem? At that time, you can use this one. Indexing. Then we try to use such a key to organize the index. So first one is a primary index. Primary. Let me use this slide. So this is the data file, right hand side. I think I need to replace the battery. It's almost no. I'm not sure I need to have the battery. Oh yes. I have. If you go to any federal office, you need to pass through the security gate. At the time, if you have any electronic device, you need to show. I have at least 15 different electronic devices, including this one, connector, everything. So the security guy said it looks like the Radio Shack. So, why is it changing? Something weird? Even it's still not visible. I don't know what happened. So usually better than this. Anyway, the right hand side is the what? Our data file. It's a non-ordered file or ordered file?
Ordered.
It's ordered by key. Let's say the key is a primary key. You can see the top. Primary key is the name. We are going to use the name. Which is not good, but this guy used a name as a primary key. Then ordered by the key. Without using anything, so we can use the binary search. At this time, so let's say how many blocks we have? 1, 2, 3, 4, 5, 6, 7, 8. We have the 8 block. Average, how long it takes?
3 times.
Log 3 based on 2. Not the number of record, because keep in mind, when we measure the performance or I/O, we are not going to count data by data. We are going to count block by block. That is, I spend a lot of time to explain about the blocking. Block is the basic I/O. Even though you read the one data, entire block, one block will be read and cached and managed. So because of that, it's a block by block. So even though without using the index, when we are using binary search cut in half. Okay. Then, for example, I try to access the Adams Jones. Adams Jones is the top of the island. Adams Robin. Adams Robin is the second of the second block. At that time, cut in half. First one I/O, then the cut in half. That is the Adams Jones. Then finally, we can access data to equal or less than 3 I/O. So that is the binary search. The question. Adams Robin is the second row of the second block, each block. Do I need to read it again or not? How can you search the Adams Robin in one block? how long it takes? You need to use
Linear.
linear or binary search, either of them. However, that will not be counted. Why? It's a binary search or linear search, it may be. Keep in mind, it's a block I/O. So entire block will be loaded into the cache. In a cache, it's just the piece of cake. You can ignore that overhead. And binary search or linear search, because it's happened in the memory. So once the data is in one block, once you find the block that includes the data you want, then the other you can ignore from now on. It's not from now on, it's every application has the same thing. So once you load into the memory the block, there is no more cost. Almost you can ignore such an overhead. So that is how it works to search the data using the only ordered file, using the key binary search. But if we index, what we are going to do is index first row of the data. In this case, Aaron Ed, Adams John, Alexander Ed, the Ellen Troy, and so on. Which is called anchor data. Anchor means it's a kind of a representative. We can have the one representative. Why? Because data are sorted. If we find, for example, I'd like to find Adams Robin Adams. That belongs to the Adams Jones block. So if we can find Adams Jones block, then it's done. Okay? So we select the such anchor record, representative record, then order, like the Aaron Ed, Adam Jones, Alexander Ed, and index. Only anchor. Then index is key value plus 1. Pointer, address. Then each block pointer point the address of that block. Okay, then I'd like to search the Adams Robin. How can you search the Adams Robin? Using index. First, going to the index. Index also based on what? Block. Okay? Same thing as the data file. It has the index file, has the number of block. Each block has number of index key entry. So, among the index key entry, how can we search the Adams Robin? Binary search. We can do the binary search. Then you will find it's bigger than after Adams Jones and before Alexander Ed. Right? Adams Robin is between Adams Jones and Alexander Ed, which means it belongs to the second block, Adams Jones. Then Adams Jones has the pointer, and using that pointer, you can access the block that include Adams Robin. That's how many blocks? 2 blocks. Always the 2 blocks. It may be longer if you have the more. Okay? If you have the more the data, you have the more indexed block, but indexed block will be smaller. It will keep the more record. Okay? So eventually you can search the data using this is called the primary index. Primary index use the primary key value and only anchor data. Question. Whether is this the dense index or non-dense index?
Non-dense.
It's a non-dense index because we keep the only anchor data, one data of each block. So then, I'm not going to use this slide a lot, but you can evaluate. I'm not sure whether that's really fast using index or not. So we need to evaluate how much fast. For the evaluation, we will use some simulation data. Then, but we are going to use how to measure the performance of the searching. Time, but it's not possible to check the time. There are a lot of things happen. Not only read the data, but instead,
Time
What-
complexity.
what is the time complexity? So mathematically, we prove the log based on log the version 2 is the better because we have less number of the index blocks. Then to simulate, what is the most expensive operation when you read the data? You need to transfer, you need to seek time and everything. Finally, how many blocks you read? So in other words, we are going to count number of blocks. Later, even though when we measure the performance of the database system, we are going to consider number of blocks you need to access. The more block you access, it's slow. The less block you access, faster. Okay, then, for example, this is an example. So, we have the B, capital letter B means what? Block size, this one. This size. Block size is 1K, and number of block, number of record, how many data? 30,000. And the average record length is the 100 byte, which means what is the blocking factor in this case? Blocking factor means average number of record per block. How many record? 100? Each record 100 byte. So one block is 1K. How many? 10 point little bit is a 10. So that is the blocking factor is a 10 record per block. At this time we are using the floor like this. Okay? Because it will be span. So we will consider the 10. Then, which means we can calculate how many blocks. The 30,000 divided by the 10, that will be 3,000 blocks. So, first, if you are using linear search, how long it takes? Linear search, brute force. 30,000. If you are not lucky, 30,000. If you are lucky, one block on average. On average, 1,500 a block. Okay. So do you remember the complexity of the the linear search is the number of blocks divided by 2. So it's 15,000. However, this is the order 5. The order is by the primary key, so we can use the binary search. If you are using the binary search, how long it takes? Log 3,000 based on 2. Right? It's a logarithm for the binary search. That is the 12 block access. At this time, we are using floor. Why? Even though 11.1, that means it's at least you need to access one more block. So it's a floor. The function is a 12. Then, what if we are using the primary index? Primary index. So for the primary index, we need to know blocking factor of the index. So it's the same mechanism. So block size is the